Have you ever wondered what a quantum computer really is and why so many scientists and tech companies are so excited about it? Let's dive deep into it in a way that actually makes sense. First, let's start with what we already know. Regular computers. Your laptop, your phone, the servers that run Google or Netflix, all of them work using bits. A bit is the smallest unit of information, and a bit can be in one of two states, 0 off or 1 on. Every app you open, every message you send, and every video you watch is, underneath it all, just millions or billions of bits flipping between 0 and 1 at incredible speeds. Now, a quantum computer plays by completely different rules, the rules of quantum mechanics. Instead of bits, it uses qubits, quantum bits. And here's where things get weird and exciting. Unlike a regular bit, a qubit doesn't have to be just 0 or 1. It can be both 0 and 1 at the same time, thanks to a phenomenon called superposition. Think of flipping a coin. A regular bit is like a coin landing on heads or tails. A qubit is like a coin spinning through the air, being heads and tails simultaneously until you catch it. Because of superposition, a quantum computer can explore multiple possibilities at once. This means that while a classical computer tests one solution at a time, a quantum computer can work on many potential solutions simultaneously. But there's more. Quantum computers also use something called entanglement. When two qubits are entangled, their states become linked, so that the state of one qubit instantly determines the state of the other, even if they are light years apart. Albert Einstein famously called this spooky action at a distance. Entanglement allows quantum computers to perform complex operations that classical computers can't easily replicate. It's like having a magic pair of gloves. Put one on your hand, and the other instantly matches its movements, even if it's halfway across the world. Now, let's talk about how quantum computers actually perform computations. In classical computers, we have logic gates like AND, OR, and NOT that manipulate bits. Quantum computers have something similar called quantum gates. Quantum gates manipulate qubits, but they can do far more complex transformations than classical gates. By applying sequences of quantum gates to qubits, quantum computers can create sophisticated algorithms. One famous example is Schur's algorithm, which could, in theory, crack widely used encryption systems, a task that would take classical computers millions of years, but that a powerful enough quantum computer could do much faster. Another example is Grover's algorithm, which can search through unsorted data way faster than any classical method. But here's the catch. Qubits are extremely delicate. Even the slightest bit of heat, vibration, or electromagnetic noise can cause them to lose their quantum state, a problem known as decoherence. That's why quantum computers are kept in super-controlled environments. They are cooled to temperatures colder than deep space near absolute zero, around minus 273 degrees Celsius. They are isolated from vibrations, light, and magnetic fields. And even with all that, they still require something called quantum error correction, complex methods to protect information against errors caused by decoherence. Today's quantum computers are still in their infancy. The devices that exist now, from companies like IBM, Google, and startups like Atom, are called noisy intermediate-scale quantum NISQ devices. They have limited numbers of qubits, and they make a lot of errors, but they're powerful enough to start experimenting with. And here's why quantum computers are different from just super powerful supercomputers. A supercomputer is basically a lot of classical computers linked together, solving problems faster by working in parallel. But a quantum computer doesn't just work faster, it works differently. It tackles problems by exploiting quantum properties like superposition and entanglement, allowing it to solve problems that might be impossible for even the best classical computers, no matter how much time you give them. What kinds of problems? Designing new drugs by simulating molecules atom by atom. Optimizing massive systems, like logistics, finance, or traffic flow. Solving difficult math problems behind modern cryptography. Discovering new materials, like superconductors that work at room temperature. Right now, researchers are still figuring out which problems quantum computers will absolutely dominate. But the possibilities are huge. In short, regular computers use bits, 0 south and 1 south. Quantum computers use qubits, 0, 1, or anything in between, all at once. Quantum computing isn't just about speed. It's about unlocking entirely new possibilities. We are at the very beginning of the quantum revolution, and just like the first computers from the 1940s, today's quantum computers are big, experimental, and a little clunky. But give it time. One day, quantum technology could transform the way we solve the hardest problems on Earth.